Welcome back. So we continue the discussion on this structural analysis or the basic structural analysis. Now we would like to see how this we can correlate with the blade oscillations and the centrifugal stiffening. So what we would kind of try to see is the looking at this blade oscillations, okay, and centrifugal stiffening. So what we would do is that essentially the blade oscillations mostly occur in clockwise direction. That is forward and backward. So if I have a unit like so, the blade can go like that, blade can go like that. So that's essentially the forward and backward operation. So that's typically how the blade oscillation takes place. However, rotation, the blade and has higher frequencies than it would have without rotating. So that means since the blade actually oscillates flapwise, this gets stiffened, and since the blade gets stiffened, they can have higher eigen frequencies than it would have without rotation. So how that happens? Let's say, let's see how that happens. We can take an situation of rotating hinged beam, obviously no elasticity. So let's say we'll have, and this is how okay. So this would be P FC. This is rigid beam and that hinge. Okay. So what we can have moment of inertia I mu r square dr. We have poised oscillation angle phi you have restoring moment m of phi. So what we have, I phi double dot equals to m of phi. So that is how this. Now this restoring moment m of p. So this comes from centrifugal force. So which we can estimate as m of phi 0 to r mu r omega square r dot cos phi sin phi r dr. So this is 1, this is phi. That comes from the, I mean, essentially this one can write from small angle approximation. From there we can write this kind of situation. Okay. So what we have then, minus phi omega square 0 to r square dr minus phi omega square I. So now if we put this back in this equation, and then what we have, I phi double dot equals to minus omega square I, that omega t. So it means that eigenfrequency equal frequency. So that's what you can get. So now one more thing that you can say, that let's say a rotating beam, torsional thing. Okay. So if I draw this is angle phi, so this is torsional spring. Okay. So here the spring constant is k. Okay. Now the natural frequency that you have, natural frequency or the natural resonance omega in r root over k by I. M of phi is minus omega square I phi minus k phi. I phi double dot is minus omega square high Kp, and then what we have, omega r square, omega nr square plus omega square. So this term is centrifugal deepening. Okay. So this is where the the blade actually, when this oscillates forward and backward motion, so essentially the flapwise motion, this can actually stiffen. So we have seen from a hinged beam analysis that if it is rotating, which essentially a situation that happens in your rotor blade, that when it rotates, that creates that kind of situation. But we said that since the blades are basically oscillate like this, but at the same time they are also rotating. So one hand you have rotation along with that, so flapping. So this is kind of an like this, and they can rotate. So that's make things quite complicated. Obviously, you can see that the design procedure of the rotor blades are quite involved and multidisciplinary, or rather multi-skill analysis one has to carry out to come up with proper design parameters and things like that. And now, since we have, so this kind of gives you why this, so the stiffening happens, which is because of your centrifugal stiffening. That's these are giving an broad idea about these things which are kind of take into account while talking about. So, what we would like to take this forward is now this analysis. Essentially, we want to look at that wind turbine rotor dynamics analysis. Okay, where we can look at some kind of an. So far, in fact, we are talking about that only, and we started with the mm, kind of types of load. If we recall that what we talked, so we talked about types of loads, which could be steady load that can include static and rotating, which could be cyclic load. You can have transient loading, which essentially includes the impulsive loading, stochastic loading. You have resonance induced load. So these are the loads we talked about that goes in the rotor, and obviously that kind of expose to the. So while talking about that, those steady loads are the ones that do not vary over relatively longer period of time. Um, so they could be either of static or rotating. I mean, for example, a steady wind blowing on a stationary wind turbine that would induce static loads on various parts of the machine. Uh, and at the same time, a steady wind blowing on a rotating wind turbine rotor, while it's generating power, would induce steady loads on the blades and other parts of the machine. Then we had the cyclic loads, which are vary in a rectangular or periodic fashion. Obviously, here we are talking about loads because these are connected or arise due to your rotation of the rotor. So cyclic loads arise as a result of such factors as the weight of the blades, wind shear, yaw motion. Also, cyclic loads can be associated with the vibration of the turbine structure or some of its components. Okay. Then you can have transient loads, which are essentially going to be time varying, which is again arises to some temporary external event, and there could be some oscillations which could be associated with the transient response. But obviously, it's not amplifying, then it decay with time so that the system becomes stable and all these things. Obviously, sudden impulse which could happen due to sudden change in wind speed or due to some mechanical component. Those impulse load can also be transient and for a short duration of time. Um, then we had talked about stochastic loads, which are also time varying, cyclic, transient, impulsive, because that primarily arises due to the turbulence in the wind, because the turbulence is a stochastic field or stochastic in nature, so kind of give rise to that kind of stochastic loading. Then one can have resonance induced loads, which are cyclic loads, the dynamic response of some part of the wind turbine, which are being excited at one of its natural frequency. This may reach high magnitudes. Obviously, any resonance induced load that has to be avoided wherever or whenever it's possible. But during operation, they may arise during under certain operating conditions or due to poor design. So one has to be. Then we have talked about sources of loads, which are coming from aerodynamic, the gravity, dynamic interaction, mechanical control. Obviously, the aerodynamics loads are primarily due to the wind turbine. So that's what we have looked at, how the aerodynamic forces can be generated and how much, what would be the. Then gravity is there, which could be a source of loads on the blades for large turbines, although it is less for smaller machines. Then you can have dynamic interactions, which is motion induced by aerodynamic and gravitational forces in turn can induce loads in other parts of the machine. For example, virtually all horizontal axis wind turbines allow some motions about an yaw axis. While the yaw motion occurs, while the rotor is turning, there will be an induced gyroscopic forces. If the yaw rate is high, then these forces could be quite substantial and can have a significant impact in the. Then the mechanical control, which is can be sometimes the source of significant loads. For example, starting of turbine, which uses an induction generator, or stopping of the turbine by applying a brake and things like that. Now, I mean, then there are effects of loads because this loading experienced by a wind turbine uh, are quite important in two primary areas. One is that ultimate strength, and second is the fatigue. I mean, wind turbines sometimes occasionally experience very high loads, and they must be able to withstand those loads. Typical normal operation, which is kind of accompanied by widely varying load due to starting, stopping, yawing, or passage of blades through continuously changing winds. But those are normal. But these varying loads can cause fatigue, damage in missing components, and sometimes that component may eventually fail at much lower load than it would have been when new. So that means in the design, one has to be very careful that how much strength it can withstand, and then so that these damages can be caused. So this is where we have used our fundamental principle of solid mechanics or structural. So where we have looked at these different forces which could arise due to rotation. So inertia forces. I mean, since they are rotating, I mean, for example, the effect of centripetal acceleration associated with the rotation of the rotor is accounted for by the inertial centrifugal force. So due to the rotation, then we have had bending of cantilever beam. So we looked at the beam bending equation. So these are coming from typical strength of material analysis. Why this is important? Because the blade is basically cantilevered beam. So that is what we have discussed. And then we looked at the bending moment, the equation of the bending moment, then maximum stress, all estimated from there. Then we have talked about or rigid body planar rotation. So have this two-dimensional rotation which acquires angular momentum. Obviously, you have the due to this angular momentum, you could correlate the by law. I mean Newton's law of motion. The magnitude of sum of moments could be, I mean, the J alpha or mass moment of inertia into alpha. Those are the things one can, I mean, obviously you can correlate with the angular acceleration, angular rotation. Then you can have rotational energy or frequency. Then you have these basic gears and their mechanism. So because in the nacelle or the housing, you have two different kind of gears. One is in size and larger, another one is smaller, so that the speed ratio varies. Those things that is there. Then obviously important aspect of it is gyroscopic motion, and which is quite important in terms of for design of wind turbine, because this is something very, very crucial. The reason being the yaw of the turbine while the rotor is spinning uh, can result in significant gyroscopic loads. So the gyroscopic motions mm, can have significant impact on the so obviously this gyroscopic due to this gyroscopic motion, the loads and the rotations, the moments would arise, those things can be also estimated and should be considered while then we have looked at vibration. So we kind of looked at single degrees of freedom, which is as a spring mass damper system, then multi degrees of freedom. And then again, when you have a system which is vibrating, then you have eigenmodes, eigenvectors, and then try to see when you talk about the both tower nacelle and the rotor blade, their blade passing frequency, rotational frequency, and most important thing, all this analysis is that one has to understand in such that it avoid it because once or because due to frequency and oscillations, there could be a structural damage. That is the thing one has to avoid. That's why this analysis that we have discussed about based on 1 degrees of freedom system, 2 degrees of freedom system, and also we have looked at kind of an vibration of cantilever, their modes, and uh, when you have hinge and rotation, so they could have obviously they are leading to different frequency or natural frequency. And then we have looked at personal systems. Okay. So many are in the drivetrain can be also modeled by a series of discrete constant by train. So these are the things that we kind of try to address using our fundamental principle of the structural mechanics. And now we'll extend this for the analysis of the rotor dynamics. Okay. So we'll continue in the next.